Hello everyone. Today I am going to talk about the quantum Hall effect. So try to understand the quantum Hall effect. First we will look uh, what is classical Hall effect. Okay, so this is the standard geometry to understand the phenomena classical Hall effect, which was discovered by Edwin Hall in 1879. Okay, so this is a metallic three-dimensional sheet, so of certain length, width and thickness. We have applied a voltage along the x direction. So these are the axes to represent the directions. So we have applied some voltage along the x direction, so current is flowing along the x direction. At the same time, we are applying we have applied a magnetic field along the z direction. So because the charged particles are moving under the influence of the applied field or applied voltage, so along the x-axis. So in presence of the magnetic field, so there is a the force, that is Lorentz force, on the moving charged particles due to this magnetic field. So because of that Lorentz force, due to this H, the negative charged particles are accumulating here and the positive charged particles are accumulating over this end. Now there is again a field or a voltage set up between because of the accumulation of these two charges. So again, because of this field, a force acting on the electron because of this field, this voltage, so that is also known as Hall voltage. So this is along this direction, and on the electrons the force due to H is along this direction. So these two forces are acting on the electrons in the opposite direction. So at the steady state, because when this Hall voltage, as the accumulation of charges increase, so the Hall voltage increase, and after a certain time, so there is a steady state when these force and these force they become equal, and then there is no more change in the Hall voltage. So this is the this voltage is known as Hall voltage. Okay, and this effect is known as Hall effect, and we can measure the Hall coefficient, which is nothing but the ratio of the applied electric field, sorry, the Hall field EY, because this is y direction. So the field which is developed along the y axis, along the y direction, so this is the Hall field, Hall to Hall voltage. So this is Hall field divided by the current which is along the x-axis, so this is Jx, and the applied field. So this is Hall coefficient, and we can easily calculate this, and we will get this Hall coefficient, which is nothing but minus 1 by Ne in SI unit and minus 1 by NEC in CGS unit, where N is the number of electrons per unit volume, E is the charge on electron, and C is the velocity of light. So one more thing I would like to discuss here, that if we look at the, so this is Hall coefficient, and if we look at the ratio Ey by Jx, this is nothing but the inverse of conductivity 1 by sigma, okay, which is resistivity. So E by Jx is actually the resistivity. So resistivity is nothing but the Hall coefficient multiplied by B. So so Hall coefficient multiplied by B gives you the resistivity of the this material along this y axis, because here your E is along y axis. So Ey by Jx, and there is another resistivity which we can calculate from Ohm's law. V is equal to IR. So R is V by I. So this is actually along this axis. So this is another resistivity which is of the material. Okay. So this is what uh, I was talking about. So this is rho XX is resistivity, that is longitudinal resistivity, and rho XY, which is transverse resistivity and is also known as Hall resistance. So transverse, because here the resistivity is along, we are measuring along the Y axis, which is perpendicular to the x, the direction of the current, and this is the resistivity of the material we are measuring along the direction of the current. Okay, sometimes is also known as magnetoresistance, but this is not very common. So because this magnetoresistance term we are using for the materials in which the resistance is field dependent, is magnetic field dependent. But in this case, in general, all materials do not show the magnetoresistance effect. So, so, so in general, this is actually independent of magnetic field, this resistivity. Okay, so we can see from here the resistivity is nothing but 1 upon n e nu, where n e mu, where mu is the mobility and n is number of electrons per unit volume, ehr. So this term is constant, actually is independent of b. So this resistivity is here independent of b. Okay, so it's almost is fixed. It's, of course, is temperature dependent, but here we are looking the field dependence of resistivity. So again, one more thing I would like to mention here, we are resistivity we are talking about because it is the property of material and is independent of the shape and size of the specimen. So if you look at the resistance and resistivity relationship, so they are related. Rho is R, resistance is rho L by A, and if you look at the dimension of the resistance, so this is rho, dimension of rho multiplied by L, and 2 minus d, where d is dimension. So for 3-dimensional system, 2 minus 3 is actually minus 1. So rho multiplied by the dimension of length to the power minus 1. Okay, so this also we can get from here because the dimension of area is L square. So here rho L to the power minus 1. Now for 2-dimensional system, 2 minus 2 is 0. So resistance, the dimension of resistance and resistivity is actually same for 2-dimensional system. So why I am discussing here the resistance and resistivity for 2 dimension, that you will understand in the next slide. Okay, so one more thing uh, about the transverse resistivity. So as I had discussed in the first slide, that the transverse resistivity is actually nothing but Hall coefficient multiplied by magnetic field. So that gives you the resistivity, transverse resistivity. So magnetic field and Hall resistance is Hall coefficient is 1 by Ne. So basically transverse resistivity or Hall resistance, which is, you can also say, Hall resistivity or Hall resistance. So this is actually proportional to B, because here B is coming over here. So that means with increasing magnetic field, your Hall resistivity increases. So this is shown in this graph. So this is linearly increasing with field, and the longitudinal resistivity is constant with respect to field. So no change. Okay, so this is the behavior for classical Hall effect for a system, 3-dimensional system with in presence of magnetic field, how your resistivities, longitudinal and transverse resistivities are varying with respect to magnetic field. So this is all about the classical Hall effect. Now let's go to quantum Hall effect. How your quantum Hall effect is different from classical Hall effect. Okay, so classical Hall effect, it was discovered by K. von Klitzing in 1980, and the classical Hall effect was discovered by Edwin Hall in 1879. So almost 100 years after the discovery of classical Hall effect, quantum Hall effect was discovered. So this effect was observed in low dimension systems. Low dimensions means 2 dimension. 2 dimension is basically thin film, means we are restricting the z direction. We have only 2 dimension, x and y. In z direction, the specimen, the sample is very thin. So the motion of the carriers, charge or whatever carriers, electron, uh, in this case metals, in case of metals, there are, of course, they are electron gas. So the motion of electrons are restricted in the z direction. So we have only xy, the motion. So, and of course, we need very high field to observe this effect and at very low temperature. Okay, so this effect uh, is actually observed at low temperature. So, what is the striking feature? What is how it is different from the classical Hall effect? Now, see this graph. So the dotted line, the dashed line actually represents the classical Hall effect behavior. So this is transverse resistivity increasing with field, and longitudinal resistivity is almost horizontal with the field axis. But this is the actual that has been observed for thin films, two-dimensional systems at very low temperature in presence of high field. So now the there are two things. For transverse resistivity, we have plateau regions, then there is a sharp drop, and then plateau region, and then sharp drop, and then plateau region, and like that. So basically, we don't have all possible value of resistivity. We have this value, this value, this value, and so on. And interestingly, these values are actually the in units of h by e square. So this is multiplication of this value is multiplication of h by e square. This value is multiplication of h by e square. This value is multiplication of h by e square. So h is Planck constant and e square is charge constant. These constants are universal. So that means the value of transverse resistivity is actually universal. Is independent. These values are independent of material. So because I 1 2 3, these are just integers, so they are in some sense they are integral multiple of h by e square. So they are independent of material, they are independent of shape and size of the sample. So that is the most striking feature of this effect. And at the same time, if we look at the longitudinal resistivity, you see most of the time the value of this longitudinal resistivity is 0. So that means they are in this range, they are behaving like a perfect conductor. And at this point, the resistivity is very very high. So they are showing peak. So basically, as a function of magnetic field, there is a transition uh, there is transition like conductor to insulator to conductor to insulator to conductor and so on. So these are the two important features of the quantum Hall effect. So this is how your classical Hall effect is different from quantum Hall effect. So this is the expression for the transverse resistivity. You can see is given by h by e square. This is constant, and 1 by gamma, where gamma is some integer. So this is actually 1 by gamma times h by e square. So Hall resistivity in quantum Hall effect, the transverse resistivity is independent of the material, is independent of size and shape and quality of the sample. Means if there is, even if there is defect, you will get this resistivity is integral multiple of this number. How we get, why we have this kind of behavior? So this can be understand in terms of Landau magnetic subbands. This we have already discussed in the classroom. So this is the orbitals energy states or allowed states for a electron gas in k space. Okay, we have all possible k values. Okay, so this is for free electron gas. In presence of magnetic field, so the all k states are not allowed. We have the quantized energy states. So these and this, these are different quantized energy states, different levels, and these are known as Landau magnetic subbands or Landau magnetic levels, sometimes also termed as. And this is the same thing here. You see, for free electron gas we have the energy states, all allowed state, and up to the Fermi level all states are filled, and above that all states are empty. In presence of magnetic field, the continuous energy levels, they change to some discrete level, and of course the energy difference between these levels is directly proportional to B. So this is actually the same thing. So here all K are not allowed means all energy states are not allowed. We have certain energy, certain K values are allowed only. Okay, so these are the energy levels. So these are the actual Landau levels, and it depends on B. So B1, B2, B3 are different magnetic field, and you see the gap is different in these cases. Okay, so now we can calculate the so uh, so we can simply calculate the area between the two circles, two successive circles. So this is simply we can calculate pi delta k square, and this is 2 pi eb by hc. So here all are constant except b. So if b is fixed, the area between the two circle is constant. Okay, and area between two circle we can increase by b. So this is the same thing. Area, if we are increasing increasing this radius means we are increasing this gap. Okay, so this delta we are increasing this gap, so we are increasing, that means we are increasing this the energy between the gap between the two energy levels. Okay, and how many number of states which can corresponds to the same energy level. So that is basically the degeneracy of this energy level, energy state. So this we can simply calculate by, so the area, this area, okay, we can divide by the the area required for one state in k space, so we can get this number. So this is actually the degeneracy or the number of orbitals in a particular Landau levels. So this we have already discussed in detail, and you can go through your notes. Okay, so again, so from this the number of orbital degeneracy what uh, we had discussed in the last slide. So in one Landau level is given by EBHC multiplied by L square. So this is the same thing, EBHC, okay, multiplied by L square. So other terms are cancelled. So this is the degeneracy, means number of states, number of orbitals that corresponds to one Landau level, where L is nothing but the dimension of the sample. So we have XY dimension because in Z dimension the sample is very very thin. So we have, so here I have assumed that X and Y dimension of the sample uh, dimensions are same for this sample. So in case of the dimension is different for L X and Y direction, you can have LX LY like that. Now if we want to calculate the number of states per unit area, okay, so we can multiply, this is area, actually area of the sample. So d by L square is nothing but eb by hc. Okay, so this is the number of orbital state, number of states per unit area, and let's say this is n naught. Okay, now consider this situation because that when J Landau levels are completely filled, means because we are doing the experiment at low temperature, so up to Fermi level all states are occupied, and above that all states are empty. And suppose that, because now the number of electrons up to the Fermi level, they are distributed in the different Landau levels. Now for some, for because we are changing B, so B means we are changing the degeneracy of the energy levels. With, if we change B, degeneracy will change. And for some B we have the, suppose the Landau levels, jth Landau levels, means first, second, third, fourth, like that. Suppose up to J, the Landau, all Landau, the all orbital states of jth Landau bands are completely filled. Okay, in that case we can simply calculate the number of electrons. Okay, in that case, which is nothing but the number of electrons in each Landau level is n naught multiplied by the jth Landau level. So this will give you the number of electrons or number of states per unit area. Okay, now what is Hall resistance? We can calculate Hall resistance is actually the B multiplied by Hall coefficient. So Hall coefficient is 1 by NEC. If you, C is coming because you can go to slide 1 and CGS For CGS system, RH is 1 by NEC, where N is the number of electrons per unit volume and B is the applied field. N is number of electrons per unit volume for 3D case. But here we have considered our sample 2-dimension. So we have N is actually the number of electrons per unit area simply. Okay, and this is what we have calculated here. The number of states or number of electrons per unit area is this number. So we can substitute the value of N and we can get this. So J is coming from here, J N naught is this term. So if we substitute this, we will get the Hall resistance is the same, because for 2-dimension Hall resistance and Hall resistivity, they have same dimension, so same term. So this will come out H by E square 1 by J. So J is again here, J is the Landau states. Okay, so J is equal to 1, 2, 3 like that. So it's like a quantum number. Okay, so this is integer. So now you can see that your Hall resistance is integral multiple of H by E square. Okay, so this is when all the Landau states are completely filled. Okay, or not all, jth Landau states is completely filled. Okay, so when we change the field, so after some time your degeneracy will change. Okay, and then if the degeneracy will change, and so the electron will go to new state, and your different Landau states will be the top filled orbitals, and then you have a drop and different resistivity value. It's like that. So that is how your resistivity is jumping from one state to another state. So it's quantized like behavior. Now our objective was to understand, to actually to construct the Fermi surface using the quantum Hall effect. Now from the concept of the quantization of electron orbit, we have this we have already derived this expression. Okay, so now what this equation tells us, that the equal increments in 1 by B produced the similar orbits in K space. So this is the actually the area of electron orbit in K space. Okay, and this is constant, this term. So what does it mean? That the periodicity in 1 by B is a striking feature of magneto-oscillatory effect in metals at low temperatures. So magneto-oscillatory effect means if we are measuring the resistivity, susceptibility, or heat capacity or other parameters, we have oscillatory effect, means we after certain B we will get some oscillation, then after certain 1 by B, increment of 1 by B, we will get oscillation, and that is what we are getting here. So the oscillating with respect to B. So if we have the information about 1 by B increment, so this difference, so one oscillation or and two successive oscillation, uh, the field, the 1 by B required for two successive oscillation will give you from this difference 1 by Bn plus 1 and 1 by Bn, we can calculate this S. So S is actually the Fermi surface, the area in the reciprocal space. So this oscillatory B will give you the information about S, and that S is perpendicular to the direction of the magnetic field. So if you change the direction of field, you can have the information of the Fermi surface area in another direction. So by applying field in different direction, you can have the information about Fermi surface area in different orientation. So if you club all them together, you can construct the Fermi surface of this specimen. Okay, in for this given specimen. So this is how we can construct with the help of quantum Hall effect, we can construct the Fermi surface. So this is all about this quantum Hall effect, and if you have any query, you can write to me. Thank you so much.